Hello, welcome to Expressions Video 8. Before we start, I want to just remind you to take your video notes. Those are due tomorrow with the 3 patterns on the other side. Also, that's very important, we're going to have our final unit for assessment starting on Friday, and then we'll continue it on Monday. So let's get started. In this section, 4-8, we're seeing how different representations of the same expression can give different meanings to basically the same quantity, and how we choose to write an expression can affect the type of meaning that we're trying to give it. So this is the pattern that we worked on in class today. It's example 1 on the back classwork side, and we can see the patterns growing. It's like an L shape, and we can see how many cubes are in each shape. There's 1 in the first, and 3, and 5, and 7. So it's growing. Some people mention growing by 2 every time. So if we want to know how many cubes there would be in a general picture, like a picture that is n, one of the possible expressions is 2 times n minus 1. So where might this come from? Well, we're looking at the 4th shape, n is 4, so we can see these 4 blocks here, right? We also have 4 blocks here, so that would be 2 times n. There's an n here, and there's an n here, 2 times n. Why do we subtract 1? Well, we would be double counting this block on the bottom corner. We should subtract it once because it would be counted in the vertical stack and the horizontal stack. So 2 times n minus 1 could be shown using that representation, that idea of thinking about it. Another expression could be this, 2 times n minus 1 as a quantity plus 1. So let's look at how that would be shown in one of the other images. Here's n is equal to 3. In n is equal to 3, if I circle these 2 blocks, there's 2 blocks there, and that would be n minus 1. In other words, 3 minus 1 is 2 blocks. I have those same blocks here, so this would be n minus 1. So you can see in this first part of my expression, 2 times n minus 1 shows us those 2 sets of 2 blocks. And then the corner would be counted as plus 1 because we haven't counted it yet. So it needs to be counted. This expression is equivalent to the first one. We can show how it's equivalent, but it's just really a different way of seeing the pattern and seeing the counting. Another expression could be n plus n minus 1. So I'll draw in a different color on this picture here. N is 2 in this picture I'm drawing on. And here are 2 blocks, so that would be n. And here's 1 block, and that's 1 less than 2. So that block would be counted as n minus 1. Again, it's 3 different ways of counting. We have a block of n, or we have a block of n minus 1, and we think about other blocks that may be counted or not counted. All of these expressions are equivalent. So take a second, stop the video, think about, do you understand where those expressions are coming from and why they're equivalent? So here's another example of analyzing expressions. Let's say that a yard has some rope or some fence around it, and we see that the yard has 4 sides, and each side is a distance, a length of 3x plus 1. Well, we could write this yard. It's a little bit easier of a problem to express, but we could think about it in a couple ways. First of all, this would be straight addition. Each side is 3x plus 1 long. So we're just directly showing what is the addition of all of these sides. And we would add them 4 times. It's a kind of long way of writing this expression, clearly could be simplified, but it really is what we mean by the total amount of rope or of fencing. Now, if we were to show that using multiplication, then we would say, okay, I have 4 sides, and each of them is 3x plus 1. So 4 times 3x plus 1 is a representation using the idea of 4 sides, each side being 3x plus 1. Another way we could write this is grouping, or what I mean is adding up the terms in the groups that they should be added. So we have groups that have x in them, 3x plus 3x plus 3x plus 3x, or using the distributive property, it would be 4 times 3x is 12x. That's our variable term. And then a 4. So 1 plus 1 plus 1 plus 1 is 4. Or in our distributive property, 4 times 1 is 4. So these would be 3 different ways of making meaning about the rope. The first one again shows us the total, just adding all of the sides as a long sum. The next one is showing us the 4 sides, each side being the same. And the last is grouping or adding together the like terms. So again, take a second to see if you understand where are these expressions coming from and why are they equivalent. You might want to pause the video. So, a little bit of a different topic, but still equivalent expressions. We talked about percent increase and decrease in our last unit. This problem says in Washington there's a 6.5% sales tax. If an item in a store normally costs $D before the tax, just some amount of dollars, maybe $10 or $100, what is its cost after the tax? There's 2 main ways of writing this as an expression. First of all, we just show adding the tax. So it originally costs $D. That's its original price. And then we would add to that the amount of the tax. As a decimal, 6.5% is 0.065. So multiplying that by the price, D, then that would be the tax. So original price plus the tax would show us what's happening to add the tax. Well, how else can this expression be written? It can be written in a slightly different way. Say, well, both of these terms have a D in them, so we would call them like terms. As we mentioned, this D, the original price, is really worth 1. It doesn't show its coefficient, but its coefficient is 1. So if we go ahead and add 1 plus 0.065, gives us 1.065. This represents the total cost, including the tax, all as just one quantity or one term. So think about that also. Do you understand that we're showing the addition of the tax in the first expression, and then we're showing it as a total cost in the second expression? It really has a slightly different meaning, and we're communicating a slightly different thing. It's important to write an expression to communicate what you are trying to say. Again, pause the video if you feel like you could use that. A similar example, but percent decrease, which again was from Unit 3. Here it says a cross-country team is attempting to have all their runners decrease their 5-kilometer course time by 4%. They're trying to get better by 4% during the season. If a runner runs the course in M minutes at the beginning of the season, so all the runners could be different, but somebody's running a certain amount of minutes, what would an expression be for their goal time, which would be minus the 4%? It's very similar to the last example. So think about it for a second. How could you write the expression in 2 different ways for their goal time. You might want to pause the video before I go on. Well, the first way that we can write the expression is by starting out with their original time. Their original time is m minutes. Now they're trying to reduce that or decrease that by 4%. So we would subtract 0.04 m. That's 4% as a decimal, 4% of their time. Well, again, how else can we write this? Well, we can communicate it a little differently by remembering that this is worth 1. The coefficient of m is 1. So we can do the subtraction because we have like terms. What is 1m minus 0.04 m? Well, 1 minus 4% is basically 96%, 0.96 m. This would mean and communicate that a runner's new time will be 96% of their old time. It would be reduced. So these expressions, again, are written differently and communicating slightly different things. One shows the reducing of the time, and one shows their final time as a single quantity or term. Please stop the video if you need extra time to think about this or take notes. This example comes from your book, and you could turn to the page. I can't remember exactly, but you'll see it right before the homework set, homework 4.8. It's very similar to the 3-act math that we did with tiling. There's a gentleman who was tiling the edge of his mirror. It says some middle school students will use 1-foot tiles to create a frame around a large square mural painting with side lengths of s feet. 3 students each wrote an expression to determine the number of tiles needed. Are these expressions equivalent? So the first person wrote 4 times s plus 1. And they're explaining their work down here. Each section, and the section is not the entire top and not the entire side, but it is, sorry about the interruption. The first student saying 4 times s plus 1. It's not the whole top length. S represents the distance of the painting, so kind of the inner square here. But s plus 1 is that distance of the painting plus 1 square. You can see that repeated 4 times around the edge. The distance of the painting plus 1 square. So how else could it be done? Well, the second student says, I have s plus s plus s plus 4. This is even clearer to see, and I think clearer in the picture. There is one length that's a long tile or a long set of tiles, which is s, the distance of the painting. And we see that repeated 4 times throughout the shape. And then we clearly have 4 corners. So the corners are plus 4. The third student is saying that the top and the bottom of the frame could be thought of as s plus 2 and could be a longer rectangle that includes the 2 corners. And then, since we've already counted the corners, the other 2 sides could be thought of as just the interior distance of the painting, which are s. So 2 times s plus 2, the top and the bottom, and 2 times s. All 3 of these expressions are also equivalent, and we should be able to use properties, the distributive property combining like terms, the associative property, the commutative property, to show why all of these expressions are also equivalent. Now there could be mistakes made. We could find some expressions that might not be equivalent, but these are. And similar to the first example, it's a different way of seeing the pattern or of counting. Please stop the video if you need extra time to look at this example. Finally, we did this earlier in our section, but returning to it at the end, how many ways can we rewrite an expression? This is one of our warm-ups, and it was also in a section that we did early on. If I have this expression 4x minus 16 plus 8x, how can I rewrite it using all of these different strategies? Combining like terms, uncombining like terms, factoring, the commutative property, or the associative property. Think about how you would do this before I show you some of the results. Please stop the video. So beginning with combining like terms, 4x and 8x in this expression add to 12x. Those are the only two like terms. 12x minus 16. The minus 16 cannot be subtracted from 12x because 12 times an unknown number is an unknown amount. We can't subtract 16 from that. B, uncombining like terms. This could be done in a lot of ways, but I've decomposed negative 16 or minus 16 into negative 10 minus 6. That's another way to think about negative 16. I'm uncombining, I'm splitting apart the negative 16. Factoring. Factoring the original expression, the GCF, or the greatest common factor, would be 4. 4 goes into 4x, 4 goes into 16, and 4 goes into 8x. So the greatest common factor is 4, and then we find the result. The commutative property, this means to switch terms around. So here I've just reversed the order of the first two terms. We could reverse any order, but the first two terms have been swapped. Now instead of 4x minus 16, we have negative 16 plus 4x. And finally, the associative property. Associative property means to group. All I've done here is put a grouping symbol, parentheses, around the last two terms, which says let's add those first rather than adding in the order given. Please think about these 5 different ways of rewriting the expression. See if they make sense to you, and stop the video if necessary. Thank you for watching the last video in this series, the last video in our unit, and possibly the last video for our year.